Okay, let's start again. Good afternoon, everyone. I hope you ate well. Welcome to this second session of talks. We are here to talk about future network and services, and we will have 3 talks. So I will let the floor to Andrea, who will present resource allocation.
Thank you. Do you hear me well? Okay. There is a bit of noise. Okay, maybe here it's better. Okay. Okay, thank you very much. So I'm Andrea. I have to take my slides again. Yeah, because there is a mismatch. Okay, now it's good. Okay, so I am Andrea Araldo. I'm associate professor at Télécom Paris, and I'll talk for 15 minutes, I hope, about resource allocation for multi-tenant edge computing. So the high-level view of my talk is the classic one. So on the one side, we have users that want to consume services that can be of different natures. We can have entertainment services like Netflix, YouTube, etc. In the future, we may have other kind of services of low latency type, like autonomous driving. So new service providers could be car manufacturers or road authorities and agency, etc. And in the middle, we have the network operator trying to connect the two. So this high-level picture has been implemented in different ways over the years. So originally, the services were deployed in centralized locations, and all the users had to connect to these locations. Nowadays is the era of cloud computing, so the services are replicated in different locations all over the world, and so users can connect to the closest location. And edge computing is pushing this concept even farther, deploying services at the edge, so very close to the users. What is the edge? So edge nodes could be central office of a network operator or a base station, or even an access point into the households. Okay, so in these edge nodes, we can deploy computational resources like CPU, memory, RAM, and we can run a part of the services directly there, and users can consume the service directly from the edge. So this has obvious advantages, that is reduced latency, and also less upstream traffic, because most of the requests can be served directly from the edge nodes. One example of edge computing that we maybe use every day, even if we don't notice, is represented by Netflix Open Connect appliance. This is a physical server that Netflix installs in some of the access networks of operators. And Netflix can control this box remotely and can decide which content to push there in order to serve the most popular content directly from the edge. So this works very well, but of course this has a lot of limitations. First of all, imagine if now hundreds of service providers come each with their own physical servers to install into the access network. This would be unfeasible, very cost prohibitive to install and to maintain. And also we cannot install hundreds of boxes like this into the access points of users, okay? So this is the current status of edge computing, but this is not future-proof. So what we claim instead is that network computing resources should be in the hand of the network operator. So it's the network operator who should have installed these resources in the edge nodes. These resources should be virtualized by the network operator and opened to third-party service providers. So the network operator should partition these resources and let service providers do what they want with the allocated resources. So in this sense, the network operator should transform itself in a micro cloud provider, and not only being a pipe like today, moving back and forth bytes, but also providing capabilities for running services at the edge. And so this is a business opportunity for network operators. And this is the only way in which low latency applications can run at the edge. So in our vision, this is the future of edge computing. So in this context, the problem arises of how we decide how much resources we should give to each service providers. So the problem of resource allocation arises, and this is what we studied in these years. And we propose two families of approaches. One is data-driven, and the other is called MORA, multiple option resource allocation. So let's start with data-driven approaches. This is joint work with KTH. So for simplicity, let's focus on one resource only, storage. So on the one side, we have users that request content. And then we have storage deployed at the edge, so we can do caching. And we assume the network operator can partition this cache in different segments and give each segment to other service providers like Netflix, YouTube, and let them decide what to store in their allocated segment. Then if the requested content is in the cache, it is served directly at the edge. Otherwise, it must be retrieved from the cloud or from the origin servers, generating upstream traffic. And so, the network operator has to pay for this upstream traffic. So this is why we assume that the goal of the network operator is to find the right cache allocation that minimizes the upstream traffic. So the problem is challenging because we assume we know nothing about the traffic itself, because traffic is encrypted, so nobody can understand what are the objects that are requested. Okay, so we have to resort to some black box optimization. So we have to optimize a function, minimize a function of which we know nothing. And for this reason, we resort to data-driven optimization, which is optimization that is not based on models, because we don't have any model, we assume, but is based just on measurements. And the only measurement we assume we have is the amount of downstream and upstream traffic. Just by monitoring these two quantities, we want to find the optimal allocation that minimizes the upstream cost. So we propose two two strategies. I will talk more about the second, and only about the second, that is more a preliminary work, and that is based on reinforcement learning. So in this case, we have a set of states where each state is a cache allocation and actions. So an action is a perturbation of a state. So it's a change of the allocation. For instance, this action here is giving delta slots to the first service provider and is removing delta slots to the third, and so on and so forth. And then we assume that we have an instantaneous cost that is the upstream traffic measured every second, and we have a Q table. So what is a Q table? So for every allocation and every action, the Q table tells us an estimation of the cumulative cost we may expect. We use the Q table to drive our optimization. So if at a certain time slot we start with a certain allocation, we see into the Q table what is the best action, that is the one that minimizes the expected cost, and we apply this action. In this case, we are giving delta slots to the yellow service provider. Okay? So we modify the allocation accordingly, And we measure again the upstream traffic. Based on this measurement, we update the Q table. And we do it over and over again. So we see here why our approach is data-driven, because it is based on a knowledge that we construct by measuring just the amount of traffic. So we do a sort of trial and error at the beginning. We perturb the cache, let's say, almost randomly. But once we start to interact with the system more and more, we refine our knowledge so that our decisions become better and better. Okay, and this is classic reinforcement learning, okay? So I want to emphasize that usually reinforcement learning is applied offline, meaning that people assume they have a model of the system, a simulation model, for instance, and then they interact with this simulated model millions of times, thousands of millions of times, so they can have at the end a good Q table that they can apply on a real system. So we place ourselves instead in a more challenging situation, because we assume we don't know anything about the system, so we don't have any model, any simulation model. We can only interact with the real system while it is up and running. So in this sense, we use reinforcement learning in an online fashion. So we cannot perturb the system millions of times, because every time we have to wait 1 second to measure the consequences of our perturbations. And also every time we do a perturbation, we pay an additional cost. Indeed, for instance, in this case, we are giving delta slots to the yellow service provider, and in order to fill these the slots with new content, the yellow service provider has to download content from the central location. So it has to produce spurious traffic that sums up to the user traffic. So we have, let's say, additional costs that we have to pay in order to learn how to optimize the system. So we need to be more parsimonious with respect to classic offline reinforcement learning. Despite these difficulties, preliminary results show that we approach in a reasonable amount of time the theoretical optimal allocation. Okay, I have 3 minutes. So I will talk now about another approach to solve the same problem of resource allocation in edge computing. That is called MORA, Multiple Option Resource Allocation. MORA in Italian is BlackBerry. Okay? And this is joint work with the University of Catania. In this case, we assume that service providers are organized as a set of microservices. So, for instance, the service provider 1 may be a content delivery network, and there could be one microservice providing transcoding, another microservice providing authentication, another providing video streaming. So each microservice does a very small piece of the application. And this is actually how Netflix works. It launches hundreds of thousands of containers every day. So we assume service providers are organized this way, and each microservice has requirements in terms of resources, memory, CPU, or others. And on the other side, we have our edge nodes with resource capacity. So deploying a service in the edge nodes simply becomes deciding which microservices to place in the edge nodes. So far, so good. The novel, let's say, idea we propose is that classically it is assumed that every service provider can work under one and only one configuration option. But this is not strictly true. We assume instead that each service provider can declare different ways, different configuration options to run at the edge. For instance, this service provider may be running transcoding, authentication, and video streaming all at the edge, But there could be also another option in which only 2 of these functions run at the edge and the rest in the cloud, and there could be another set of options like this. We assume that each option provides a certain utility to the network operator. And so now each service provider declares the different options in which it can run, and the network operator can decide first which option to deploy for each service provider, and then where to place the corresponding containers. So we say that doing this, we are exploiting the elasticity, the service elasticity. That is the capacity of services to adapt to the available resources and to change their configuration according to the available resources. And here are some results we got from simulation. So you see that what is classically assumed is that one service provider corresponds to one configuration only, and the utility of the system is quite low, while if we let services express the different options so that the network operator can choose the best for each one, we can increase a lot the overall utility of the system. Okay? And in this case, the utility we assumed is upstream traffic savings. And currently we are implementing these concepts in using Docker and Kubernetes. So to conclude, okay, I'm in time. To conclude, so what I wanted to say is that in order to allow low latency applications via edge computing, we have the network operator has to deploy computational resources at the edge and let third-party service providers run what they want there. And in this context, there is the problem of deciding how much resources we should give to each of them while maintaining their isolation. And so we propose 2 types of approaches. One that is data-driven, and today I talked about the application of reinforcement learning to this case. And the other one is what we called multiple options resource allocations. And I think I'm done. Thank you for your attention. And I'm...
Thank you very much. Do we have questions?
Thank you. Andrea, for Mora, apparently you got a result that was equal to the ideal and optimal solution?
Yes.
Is it due to the fact that you're looking at a finite set of options? Because if the set was infinite, yes, would you be there? I don't think so. No,
of course not.
Okay.
So I
just want to make sure that...
Yeah, thank you. I didn't have the time to explain the details. But yeah, thank you for the question. Actually, we formalized the problem as an integer linear programming. And this program is a multiple knapsack, multiple option, and multi-dimensional knapsack problem. So there are 3 multi. And the problem is NP hard. And there is a theoretical results that says that there are not even fully polynomial time approximation algorithm. So the only thing we could do is to provide the heuristic, and in our experiments, in our simulations, the heuristic is very, very close to the optimal. This is it. Thank you for the question.
To solve this problem, which is like did you try to solve it with constraint programming?
No, because I don't have expertise in this. But
but if it works with a heuristic, it's enough. Like if you can solve it with polynomial computation, then it is really better.
Yeah, but maybe in other we tried other simulation scenarios in which we were not so close. So maybe the approach you are suggesting may be pertinent. We may discuss it later. I would be interested in this. in the coffee.
Thank you.
Thank you.
Another question?
Thank you very much for the nice presentation. I have actually a practical question. You know that there are more and more private networks to be installed, for example, for specific needs, to have like real-time access to you know, some applications. Regarding the edge cloud, as you are proposing that an operator will be offering such service, what is your opinion on this idea of having these private networks running their own edge cloud? Is there any possibility to link the edge cloud resources of the operator, public operator, and the edge cloud that will be running in the vicinity, you know, for example, a smart factory or some other application that need to have this edge cloud as close as possible to, you know, the object, for example, that needs to have some processing resource?
Yes. Thank you for the question. So we didn't think about this, and actually, it's a thought we might have, because we thought about services that are meant for users, like video streaming or autonomous driving, but not for industries, etc. So we thought only about a sort of public cloud in our hands, deported to the edge. But what you say is, in effect, could be possible in a sense to complement private and public cloud. And why not also using these kind of approaches at the edge? But in this case, we may not have the problem of resource sharing, because private clouds would have their own resources. So there would be no problems in sharing resources. So our algorithms wouldn't be needed. And so our papers wouldn't be needed. Thank you.
Thank you. We'll stop here, I think, because it's just, we are right on time. Thank you very much again.
Thank you.
So we have now Maxime on the semantic web.
I still haven't decided yet if I talk in French or in English. Est-ce qu'il y a beaucoup de... En stéphanois, je ne saurais pas trop faire. Peut-être en normand. Je suis normand à la base. Is there anyone that is not speaking French at all in the audience? 1, 2, 3, 4, 5. Okay. So let me try then to translate the slides that I actually purposely wrote in French. I'm sorry about this. So my name is Maxime Lefrançois. I'm associate professor at École des Mines de Saint-Etienne, and I will talk to you about one specific French ANR project that we have on the semantic web of things. So the main problems that we tackle here is how to transition from what we can call the Internet of Things, Internet being the network, where actually devices that have very strong constraints and you have a lot of heterogeneous protocols and information models that are connected actually. And let's try to move progressively to what we could call a web of things, where we want to use and adopt and potentially adapt the web standards on top of the Internet of Things. So there are some challenges that are brought by the moving from the Internet of Things to the web of things, including how to break the manufacturers or alliances silos that exist on the Internet of Things So you think, Bluetooth, you think Zigbee cluster libraries, you think this or that. Everyone has its own, information model and own application protocol. So how can we, like on the web, just make so that they can all work together? Second is how to process data as close as possible to the source, and in particular we are focusing on reasoning. I'll talk a little bit about that later. Some of the enablers then are that, so as you more and more know, like IPv6 is everywhere, so the Internet of Things is growing, and we can talk about internet as soon as we have some, IP. We're talking about IP in the transport layer then, with things like 6LoWPAN or SHIC. I think it's pronounced SHIC, right? Yep. Then you start to have even devices that, like LoRa devices that you can consider part really of the Internet of Things. There exists like web application protocols that are constrained, that like CoAP, which is basically binarification plus UDPification of HTTP. HTTP is like text-based. That was really easy for hackers to understand what messages your browser was actually sending to the server. But now that we are on the Internet of Things, it's a lot more complicated, and we need to compact things. And also constrained data formats, like XML, JSON. Those are also text-based. It's easy for humans to understand it and to hack it. But actually, when you want to embrace, go on the Internet of Things, you have to compress all that. So Open Connectivity Foundation or are examples of Internet of Things protocols that actually use CoAP or CBOR. Some obstacles are that there is a lot of interoperability problems, issues, due to the fact that there is so many standards out there and so many data models out there. So you have here a view of a landscape of SDOs and alliances made by the IoTI, Working Group 3 on interoperability. And we have also constraints on the things of the Internet of Things that are typical, like in terms of processing capabilities or storage capabilities, limited or intermittent connectivity, and potentially also like batteries are limited. So our ANR project here, called CoSWoT, for Constrained Semantic Web of Things, is in this context. So let's try to go even one step further, not only use the web on top of the Internet of Things, but also use the semantic web on top of the Internet of Things. The semantic web being our main domain of research, and it's trying to make so that the web can be used by machines as well as by humans. So we want to develop decentralized and intelligent applications on the web of things, using the semantic web, and we want to target on two different verticals, two different domains, to demonstrate that our proposals are domain independent, so smart building and smart agriculture. We focus on two main problems. It's semantic interoperability and semantic reasoning. So we have INRAE, so the fusion between INRA and IRSTEA since early this year. Laboratoire Ubercurien in Saint-Etienne, l'IRIS in Lyon, Mines-Télécom, and a company named Mandeka. So just to say that ISO IEC has the Joint Technical Committee 1 has a sub-committee that you may know on the Internet of Things and digital twin, and they work among others on how to define interoperability for that. So there is transport, syntactic, semantic, behavioral, and policy interoperability. If you want to know more, interoperability being that two systems can actually exchange information and use the information that is exchanged. So on semantic interoperability, what we want to do is align the plethora of protocols and information models out there that exist. We want to use web protocols and constrained formats like CoAP and CBOR. Once we have aligned the different data models, for example, we will probably need some ontology mediation approaches to make so that a ZigBee system can talk to a Bluetooth system or whatever. And to choose those ontologies, we have actually in the past contributed to some ontologies at the W3C, so the SSN for Semantic Sensor Network, at ETSI, like the Smart Applications Reference Ontology, or in the W3C also the Things Description Ontology. So what is an ontology? I'll just step back a little. Our real domain of expertise is semantic web. We describe knowledge graphs, which are data graphs that has as an objective to transmit like real world knowledge, and so it's graphs with nodes being concepts and arcs being relations between those concepts. So here is an example of a measure about the temperature of some room, and the measured value is 20.4 degrees Celsius at a certain time and date. Other graph data model exists. For example, here graph data sets where actually you can give a name to a graph and then refer to that graph in another graph. So for example, here we can talk about this graph that is called message1 and say that actually this message1 has been conveyed by some communication with some origin and some destination. In the W3C, we use a standard called the Resource Description Framework, or RDF, where actually the data model that we use is oriented labeled graphs. We use IRIs as identifiers for the nodes and for the arcs. In a nutshell, that's it. And sometimes the end of the arc is not an IRI, but it is literal. So you have here an example of an IRI here, the identifier of a measurement, some identifier that links it to a certain value, okay, and the identifier in the middle has something to do with has simple result or something. Actually, if you go there, you will probably get some information about this, and that's the idea of the linked data. We use IRIs, and therefore, if we dereference the identifier of something, we will find some more information, and we can navigate on the web like this, actually, even if we are a machine. So when we talk about interoperability, one good way to reach interoperability is to standardize things. And so there is some work here on trying to do knowledge engineering research, because that's what we do, applied to standardization. And so as a consequence, we also have contributions in standardization. So for example, on the left, on the W3C and OGC, and on the right, this is the data model, the knowledge model for SAREF core. We also want to use RDF, so this standard, at the edge. So what does that mean? We need to potentially transform the messages that are constrained and that are flowing on the IoT into some graph representation with RDF, standardized representation, and vice versa potentially. We therefore need to find techniques to concisely convey graphs and not just 4 bytes and then 3 bytes and then 1 byte and you don't know what that is about or what it measures or whatever. And potentially mediation, as I said. Now the second big task in CoSWoT is reasoning, that we want distributed among the constrained devices. So reasoning is distributed and symbolic. So we can use different logics, like for example first order logics, but there may be more, like description logics or other. We can use rule-based reasoning, like some of you know about expert systems. It could also be inductive reasoning, and we could use techniques like graph embeddings and all. So this is not necessarily the part where I'm the most involved, but let me just say that our colleagues are interested in continuous and incremental reasoning on some kind of architecture of fog or edge architecture like this. So the idea is to lower down as close to the data as possible the reasoning capabilities, and therefore we need RDF as close to the data as possible. We've used an architecture that is standardized by the W3C that is called WOT servience, which is the concatenation of client and server. And we apply that to, as I said, building and agriculture. So let me just illustrate, well, our pilots. So we have in Lyon Tech Ladois a building with many sensors, and they want to have a dashboard to visualize in real time which doors are open or what is the temperature in every zone. At École des Mines de Saint-Etienne, we have a building that historically was built in 1920 or so, around, that we use since 1994 on 8 floors and almost 7,000 square meters. We have daily average energy consumption of 1.3 megawatt hour in winter and 0.5 megawatt hour in summer. So there is some things to optimize there. Should I stop? Or is it? And we want to develop a digital twin for that. So there is a platform technology that we call platform territoire, and here you can see a first draft of the interface where we can actually visualize the information model of the building and click on a room and get immediately, using the semantic web, some information, some knowledge about this room, who is maybe using the room or what are the neighbors of this room, and a link to an identifier of a sensor potentially, and you can go to that sensor and get the current value or get some history of that sensor. In the smart building here, in the digital twin of our smart building, what we want to focus on is on 3 objectives that are actually antagonists. I'm not sure if I can say this, but it's health management, specifically in the COVID crisis situation. You want to lower down as much as possible the CO2. Comfort management, so maybe that war of the thermostat thing, where depending on what you do and depending on who you are, well, the ideal temperature of the room you should be in is not necessarily always the same. And energy management. We have here the average daily energy consumption profiles of our building that some students figured out on the basis of open data from Enedis. And we see a peak here in the energy consumption just at midnight during the winter, and we just don't know what it is, but it's probably that our building, for some reason, is heating a lot during the night. So we want to know more a little bit about that. So we have some challenges. In the agriculture, so we use an experimental farm close to Montoldre, close to Vichy, that is owned by INRAE, and we want to, in an intelligent manner, in an optimized manner, water the fields depending on actually the moisture of the ground, but also depending on the state on the phenologic state of the plants, or depending on what actually you want to, what are your crops and what you want to grow. So that's it. At FAIOL, the institute I'm part of, so the digital twin of our building also opens a lot of potential collaborations with our colleagues from this institute, maybe in energy efficiency, low-tech innovation, statistical modeling, etc., etc. You have the list. And it's also a nice project in that we actually focus on existing, UN Objectifs de développement durable in English. Please make the translation, but it's here. Sustainable Development Objective. Thank you. So we identified a few of them, and I think it's it's a plus for the project as well. Still, well, we are still hiring due to the COVID situation when our PhDs had to stop. So we are hiring either a postdoc or, well, we have 2 postdoc positions and 1 PhD position. So if you know anyone that would be interested in this kind of projects, just don't hesitate to have a look at the website, and there is a jobs section on there. Thank you very much. That's all for me.
Thank you. Do we have question?
Thank you. Thank you very much for this very nice presentation. I have a very specific question related to this process that you have in the middle for constrained devices. Do you have a database of all manufactured electronic, platforms from Intel, Arduino, and all of them to translate into your web semantic data format?
So that would be one of the goals, to semi-automatically generate such a database. Mm-hmm. To say that, for example, temperature measurement in the Zigbee cluster library mm-hmm. is of this kind, and the operation is this to get it, and it may be different in Bluetooth, and it may be different in other things. Do you know of any such database that exists?
Yes, actually, please? There is a poster here.
Oh, very good.
I brought the poster, and we have an open source framework called Priot, where we have worked. Yes.
Okay.
It's actually having these all heterogeneous devices, and there are some interesting open source other databases where you can easily now hook into this, and then you can get any hardware heterogeneous device and do your translation to your data format.
That's excellent,
because
now we
standard,
can.
Yes, you have it's a SAREF. It's a standard.
SAREF is a standard. Yes.
Yeah.
That we may use. Yes.
But
so
I was curious.
That's very good, because we can jump to the next step.
Yeah, because I thought that probably you have something with the industry or something ongoing. But yeah, it's very interesting. Thank you.
I have one question regarding the industrial protocols like MQTT, OPC UA. Do you intend also to develop a web of things with this kind of protocols, taking some information coming from machines, from industrials?
Well, the Industry 4.0 is not a domain that we tackle specifically in this project, but we have other projects where it would be the idea, yes, as well, to investigate how the Web of Things can be, well, how a protocol binding actually can be developed for OPC UA, for example. That's another project with a region called CIRAM that I won't talk about today, and it's another colleague of mine that will focus on these kind of things. So the idea with the Web of Things is that you have the Web of Things, these standards by the W3C, is that you have a general model of what devices can offer to the network, like the properties, the actions, and potentially events that you can subscribe to. And then you have what we call protocol bindings two different protocols. So it could be a generic one for CoAP, one for MQTT maybe, and some for OPC UA. So I know that talking about OPC UA, there is a working group at the UPC UA that is focusing on semantic technologies, and some students in Munich maybe, and Siemens that were, sorry?
For Siemens,
sure, yeah, that are investigating these kind of things. My colleague Victor Charpenay, that was actually doing his PhD in Siemens in Munich, is now an associate professor with us and is looking in these kind of topics.
One last question.
I just have a question about the incremental reasoner that you're using. Could you tell us more about this? Is it a data log based or?
I'm not sure I can talk so much about this. This is our colleagues from l'IRIS and Laboratoire Hubert-Curien in Saint-Etienne that are working on this. But the idea is twofold: to try to use the storage to store some of the facts that, well, to store these facts that you have partially inferred instead of RAM, so that, well, when there are new facts that arrive, you don't need to do all the reasoning again. You can just undo what you have inferred, and then add the fact and infer back new things.
Yeah, so DRED basically, incremental inference.
Incremental, yes, reasoning.
Yeah.
So here we have slider, but no, I wouldn't be sure about specifically the name of the framework that they are working on. They have a PhD on this, and it's ongoing. So it's just after 1 year PhD. So.
And once you have the knowledge graph, how do you plan to query it, for example?
To query it?
Yes.
That would be with Sparkle, but not necessarily Sparkle. It can be just, you know, with gets.
Okay. Thank you.
Thank you very much.
Thank you.
Now we have our third talk in this session, the last one, Leonardo.
Voilà, c'est ça. Yes, so I just try to do that to see if it works. All right. So, hello everybody. So my name is Leonardo Linguaglossa, and I'm currently associate professor at Télécom Paris. And today I'm going to discuss about the data uncertainty principle. I'm pretty sure you are more familiar with the well-known Heisenberg's uncertainty principle, and I will go a little bit more in the details of these fancy new words to show an actual problem. Let me start with the context. We have already seen this morning in the talk of Professor Kaltenberger that what is happening in 5G, but more in general, we are observing a process of softwareization where we move from hardware static black boxes towards a more flexible approach based on pure software, where network applications can be deployed on general purpose hardware, maybe equipped with a regular operating system on top of which several applications, both for network and for other purposes, can coexist. Now there is a clear trade-off between the performance provided by the hardware solution and their equivalent software components that is being more and more reduced thanks to the usage of acceleration techniques that can fill the gap with respect to their hardware counterparts. And thanks to these acceleration techniques, we are seeing that it is being a real possibility of applying and implementing novel approaches for the network systems. Now, a full network can be embedded in a single server, a general purpose server, where the owner rents its resources to some clients that can act as service providers, and users can use exactly the resources provided and the services provided within this infrastructure. Now, here we can imagine that most of it is happening in software. But what happens behind the scenes? Behind the scenes, there is something like what you can see right now. So you have low-level resources, network interface cards, CPUs, RAMs, that are then allocated for the so-called virtual network functions that can be connected together to form the overall applications. Now, it is important to understand that we still need to access the data both for monitoring what is happening in the network and also to perform some advanced calculations for resource allocation, for optimizing the infrastructure. And here is where the problems arise. In the past, with hardware solutions, you could just have some data collectors, maybe which retrieves periodically the data measured from ASICs or FPGAs. And for those electronic components, it was mostly a matter of complexity and the cost of deploying such solutions. Well, in software, it's a little bit more than that, because you can still have monitoring components that may consist of pieces of code executing on a classical server. But this can cause data alteration, because such solutions are usually very invasive, and I will show you why. And they can lead to a low accuracy on the data that you are collecting, and therefore on the analysis that you can be able to perform. That is where we invented the word of the data uncertainty principle, because when you start performing measurements in the same server where you are actually deploying your application, you may see that you are observing something different than what is actually happening. In this slide, I am showing one simple virtual network function that is an L2 forwarding. So a virtual network function can be any kind of middle boxes, ranging from a pure L2 forwarding to firewalls to intrusion detection systems. And for such a very simple function, we can observe that as a baseline, I am measuring the number of clock cycles per packet needed by the function. And as soon as we start to count all packets, or maybe access some fields in the IPv4 header, or even worse, when you want to store some of the data outside, so to export it for further analysis, you are actually measuring a completely different scenario. So there is a trade-off between the data that you are looking for and the complexity of the analysis that you can perform, which limits any kind of analysis. In particular, I was focused on machine learning applications that can be deployed on software solutions. Now the context is that we can try to exploit the software nature of these novel systems to detect new correlations between what's available for us in terms of data, and what is interesting for us in terms of the behavior of the system. In particular, we try to understand how to exploit low-level data, such as the data coming from the CPU, from the NICs, to infer what is the current high-level state of the system by using low-resource inference techniques, ranging from simple machine learning to pure mathematical approaches. So I hope that this clears out a little bit the context of this work. I will now focus a little bit on the background of the uncertainty principle. I will show our approach for the analysis and evaluation of these high-speed measurement techniques, and then I will finalize with the conclusions of my talk. So this is basically a classical scenario in our domain. Ever since my beginning of the PhD, I've been working on future networks, but we can say that now they are current networks because that is what's happening right there. So you have commodity servers, network interface card, then you have the low-level resources, and you have what so-called software routers that are high-speed systems that can be used within a commodity server to forward packets, to perform virtual network functions, and they do so in a very efficient and high-speed way. Most of the techniques that are used in high-speed networks, they are targeting a specific subcomponent of the packet processing pipeline, ranging from reducing memory accesses to optimized memory allocation. But this is out of the scope of the talk. If you're interested, there is a survey on those acceleration techniques. But one of the interesting ones are very simple. They are basically polling and batching. In high-speed software packet processing, the processing of the packet, it's not handled on a per-packet basis, so you do not have individual packet arrivals, you have batch arrivals, and you have batch processing. And this particular approach, it is very effective on optimizing the CPU usage. It is a little bit more than that. So here you have a description on what is happening on in a software router. You have a network interface card, which can be a physical NIC or a virtual NIC. You have packet arrives, and there is a process that is periodically checking if there's packet here. Then a full batch is retrieved from the line card, and this is treated in software, and then the output decision is made. Now, the batching and polling approach is even more interesting because we can use that to infer some indirect characteristic of the traffic. For example, behind the scenes, the CPU is basically in one of two states, in the polling state or in the processing state. And you can use this knowledge to understand, to have a rough idea on what is going on at high level. For instance, at very low rate, it is very likely that your network interface card is empty, and so your batches are likely to be small. And on the in a high rate scenario, on the opposite side, you have large batches. So this is just an idea on how you can guess something by, let's say, an educated guess via the knowledge of the underlying system. And in fact, this is what is happening again. So you have a program that is your packet processing program, your virtual network function, that is indeed translated into low-level instructions. And those low-level instructions are executed within regular CPUs that are very complex systems with several cache and several components on the same dies. And what happens is that the low-level instructions are executed following the clock signal. So if the instructions perform in a certain way, you can maximize the so-called instruction per clock cycle, because within a single clock cycle you can be able to execute several independent instructions. If the instructions, on the contrary, are dependent one from each other, you may need to stall the pipelines and so to lose CPU cycles. More than that, if you start measuring things, you have to imagine that one of those clock cycles is immediately becoming unavailable, because instead of being allocated for the application, it is being allocated to the measurement process, and therefore you're completely altering the pipeline of the system. And in this particular case, this pipeline must be very well optimized in order to provide high-speed solutions. So our methodology is very simple, if you want. So what we try to do is to exploit at this stage some low-level information that are not directly executed at the application level, but rather they are already gathered in hardware. For instance, the CPU provides some hardware counters that you can use to guess what's going on the information. On your application. The network interface card has also internal counters which can be exported to software without the use of the server's CPU. And that is exactly what we tried to do. So we implemented in a server a scenario where we have several vector network functions ranging from Ethernet to IPv4, IPv6, or advanced functionalities. We have our CPU that is performing both the packet processing and the indirect measurement through the perf tool, and we try to understand what is going on at high level by only looking at this indirect data. What are the applications of this? So first of all, we understand how the CPU behaves with respect to the traffic that is flowing through the network. So we have several components. I'm not going into the details, but we can guess that some of the low-level information, such as the instructions and branches, are directly correlated with the complexity of the code, or the number of memory accesses at RAM level are, of course, connected with the data structures that you used, which may be linked list, hash tables, or more complex ACLs and access control list. And a nice thing that we try to do is that we try to classify the input traffic by only looking at this huge set of low-level information. In particular, we collected M CPU measurements, and we grouped into several n-dimensional vectors, where each vector includes all the low-level features from the CPU, so the number of branches, the number of cache hits, and all the others. We defined a representative vector for different scenarios. For instance, a scenario is a combination of the network traffic and the input rate. And we try to measure the cosine similarity. So in a vector space, the cosine just measures the angle between two vectors. And so when the cosine similarity is 1, this means that those two vectors are overlapped, and so they are very similar. When the cosine similarity is 0, those vectors are orthogonal. When the cosine similarity is -1, those vectors are completely inversed, basically. And we try to guess what is the traffic scenario by looking at the cosine similarity, which maximizes, which is maximal. And in fact, I'm not going to go into the details, but we can see, for instance, the scenario number 2, where we have a rate of 7.5 gigabit per second with packet size of 64 bytes. And as a function of the input rate, we can see that the cosine similarity is maximum exactly at 64 byte packets and at 7.5 gigabit per second. And we can see that we use this information to discriminate this traffic with respect to all the others that, on the contrary, are very different, because the second maximum value is this one and the third maximum value is this one, which are then discarded by the detection. So other approaches that we try to do is using, for instance, neural network models that can be deployed directly as a program within your software pipeline. And here we observe even more, not only the measurement bias, but also the impact of having in an in-network machine learning process. For instance, here you can show that the number of classifications per second is clearly going down as soon as you start having more hidden layers. And on the contrary, the accuracy is decreasing with the number of operations per second. So there is a trade-off between the accuracy that you can achieve and the performance provided by such solutions. So in conclusion, for this talk, I just gave you a global view on my work. So in the context of the network softwareization, complex measurements requires also complex approaches. And we tried to tackle those approaches by reducing the size of the ML of the problem by looking at indirect data. We focused on very simple functions, but we try now to go off with more complex scenarios and increase the number of applications. And so this is the conclusion of the talk. I hope that I am on time. Just a few words about the... so this was born as a German-French Academy program in 2019 BC, so before Corona. And where I worked with the group of Georg Karle in TUM, and now we are also opening new positions, and this gives me also the opportunity to talk about the big elephant in the room, so that we have difficulties in finding women working in this topic, and you know, women in science is a very important topic also to tackle. So if you know anything, please contact me.
Thank you very much. We might take just one question because we are a bit late. Do we have one question? Coffee time then, right? Thank you again.
We got a 25 minutes coffee break, but please be back seated in the room at 3:45. Okay?